Hello and welcome to the second part of our 30-second lecture in our Calculus 3 course. So, in this portion of today's lecture, we're going to be talking about the fundamental theorem of line integrals. So, you will recall, as we talked about a couple of lectures ago, we call a vector field conservative if it is the gradient vector field associated with some scalar valued function little f. In this case, little f is called a potential function for big F. So we discussed that just a few lectures ago. Going a bit further back, we talked about the fundamental theorem of calculus in Calc 2. So the fundamental theorem of calculus has a couple of different representations. My favorite way to think about it is if you are taking the integral of the derivative of some function over an interval from a to b, you just get back that original function at b minus the value of that original function at a. This theorem says that if you know the rate of change of little f throughout the interval from a to b, you know the ultimate displacement from a to b. The way I think about this is hiking on a trail. If you know how steep the climb is at every point along the trail, then keeping up with that gives you the total change in elevation between when you started and when you ended your hike. So, it turns out that there is a similar result to the fundamental theorem of calculus in a lot of different contexts. There's a bunch of different things that pop up in slightly different environments that look very much like the fundamental theorem of calculus. And generally when that happens, mathematicians start to get suspicious that we're actually just seeing little pieces of a larger theorem that are sort of rearing their heads in different environments. So when you start seeing the same kind of thing showing up all over the place, you start to wonder, are these all just special cases of some more deep theorem, some more fundamental theorem? And it is absolutely the case here. So the fundamental theorem of calculus, along with the theorem that we're going to discuss today, the fundamental theorem of line integrals, along with some theorems that we're going to discuss next week called Green's theorem divergence form and Green's theorem curl form, are all special cases of a deeper, more important theorem which is known as Stokes' theorem. I'll say this one more time in today's lecture, but you do have to be careful. There are two things called Stokes' theorem. There's something called Stokes' theorem at the end of Stewart, and that's not what I'm referring to when I'm talking about this deeper theorem. In fact, that version of Stokes' theorem is just yet another special case of a deeper theorem, which is also, unfortunately, called Stokes' theorem. So there are two theorems called Stokes' theorem, sort of a little one that sits at the same level as these theorems we're discussing now, and a deeper one, which all of these theorems we're discussing now are just special cases of, or particular manifestations of. So, that being said, let's discuss this first new version of this idea that's occurring to us, and it is known as the fundamental theorem of line integrals. So FTOLI for short, if you have a smooth curve given by parameterization r hat of t, where t is going from a to b, and if you have a gradient vector field, that is to say a conservative vector field which is continuous everywhere on your curve C, then the line integral of this gradient vector field along C is just given by the value of the potential function at one endpoint, the final endpoint of C, minus the value of the potential function at the initial point of curve C. So that is the formal statement of the theorem. We are going to explore what it means. We're going to first compare it to the fundamental theorem of calculus, and then we'll do some examples and sample problems to show us how to make use of this theorem in its current form. So, first a comparison to the fundamental theorem of calculus. The fundamental theorem of calculus says this, as we stated earlier: the integral of the derivative is given by the values of the original functions at the endpoints, and you take the difference of those two values. So here we have a derivative. I say a derivative instead of the derivative because we're going to start to think about the fact that there's lots of different derivative-like operations. And so there's lots of things that we might call differential operators if we were in a higher level analysis class. But there's a lot of stuff that works like the derivative. So f prime is certainly something that works like a derivative. So we've got a derivative here, f prime. We've got the original function f itself. And we've got some endpoints of the interval that we're integrating over, a and b. We can compare this statement of the fundamental theorem of calculus to the fundamental theorem of line integrals, which says if you take the line integral of the gradient of f along C, you get f itself at r hat of b minus f itself at r hat of a. Here we also have something that's like a derivative. It's going to be the gradient of f this time. If you recall, you calculate the gradient by creating a vector whose first component is the first partial of little f, whose second component is the second partial. So it is a differential type object. You are taking derivatives in some way to get from little f to the gradient of little f. So that's what's going to play the role of our derivative here. We've got the original function, which is the potential function, little f, and you've got endpoints of the region that you're integrating over. Here those endpoints are r hat of a and r hat of b, the endpoints of the curve C. And to illustrate that idea, I've drawn my curve C here together with the t-axis and shown how it is r hat of a and r hat of b are giving you the endpoints of that curve C. So in both of these cases, what we're saying is that if you integrate the derivative, whatever that may mean, the derivative over the region that's under consideration, so either the interval from a to b for the fundamental theorem of calculus or along the curve C for the fundamental theorem of line integrals. But if you integrate whatever this derivative is over the whole region, it's equivalent to just taking the values of the original function at the endpoints. And that works the same way for both the fundamental theorem of calculus and the fundamental theorem of line integrals. We're saying in some sense that knowing what the derivative is throughout the interior is equivalent to knowing the values of the functions on the boundary. Here the boundary, quote unquote, of our regions are just the endpoints of these regions because they're one-dimensional regions. When we talk about Green's theorem, we're going to be thinking about two-dimensional regions, and we're going to know something about a derivative throughout the interior of a two-dimensional region and compare that to the value of the original function along the boundary, which will be an edge of a two-dimensional region, like the circle is the boundary of the disk, for instance. So all of the theorems of this type, all of these fundamental theorem of calculus-like theorems, have to do with knowing the derivative throughout the interior. So if you know how the function is changing throughout the interior of the region, that's equivalent to knowing the original function along the boundary of the region. So it is in that way that the fundamental theorem of calculus is very similar to this new theorem that we're discussing, the fundamental theorem of line integrals, and both of these are going to be similar to the two versions of Green's theorem that we'll discuss in next week, Monday and Wednesday, our last two lectures of this course. And both of these, in fact, are special cases of Stokes' theorem, something known as Stokes' theorem. I should have an apostrophe there to make it possessive. After the S, his name was Stokes, so Stokes' theorem. But again, we have to be a little bit careful because there's an unfortunate ambiguity in that there are two theorems known as Stokes' theorem. There's one that shows up at the end of Stewart's book, and that's sort of the one that Stokes actually came up with historically. That's the little one. And then there's a deeper theorem that all of these are special cases of, which is also known as Stokes' theorem, that if I'm not mistaken was just named in his honor. He did not actually prove that theorem. It's more of a modern formulation. But it was named in his honor for he had done some work in this area. Alright, so let's make use of this beast. So we are going to be given a vector field here, f hat. And it's a fairly complicated looking one. And we're given a curve C, which is particularly complicated looking. I've got this triple level of embedded functions for my first component of my parameterization of curve C. I've got sine of the exponential of a polynomial, and then I've got a product of a polynomial and a trig function for the y component of this parameterization. So here's an f hat, and here's a smooth curve. We want the integral of this f hat along this smooth curve. So we are going to try this in two different ways. We're going to try it in the straightforward way, and we're going to fail. And then we're going to back out and wonder if there's an easier way. It's going to occur to us that maybe the fundamental theorem of line integrals will be helpful. We'll see that it is in fact helpful, and it will turn this problem, which is impossible if you just attempt it in the straightforward, obvious way, into an actual solvable problem. Not necessarily an easy problem, but a tractable problem, whereas it would have been intractable otherwise. So, if you have been paying attention in this course, it's the kind of question that I love on exams, because I can hand you a problem without any comment, and the obvious and straightforward way to attempt it might be difficult or even impossible, and a student with a better grasp of the theory will know that they can attempt it via another route. So they can use the theory to try to turn this hard or difficult problem into an easy or possible problem. So the first thing I do here, I'm dealing with a line integral, so I do want to double check myself really quick. I want to make sure that I'm aware of the fact that my integrand is a vector field. So if I'm attempting to compute this line integral of this vector field via the definition of a line integral of a vector field, I'll be using this formula. This is what the line integrals look like for vector fields as opposed to for scalar valued functions. So if I'm using this formula, I'm going to need this expression, I'm going to need r hat prime, and I'm going to have to find their dot product. And this is all non-trivial. I mean, it's trivial in that you're just plugging stuff in, but the expressions that result are somewhat monstrous. So here's f hat of x and y, here's r hat of t, so this is my x along the curve C, and this is my y along curve C. So this x and this y are getting plugged into my expression for f hat. Here's a 2y squared, that's 2, there's y squared. I've got y e to the xy, here's y e to the x times y. And then for the second component of f hat, I'm looking at 4xy, here's 4 times x times y, and then x e to the xy is the next summand. So plus, oh damn it, I missed my x expression here. So I will go back and fix that in the notes, but note that there is a typo here. There should be a x expression before the exponential, so we should have a sign of e to this polynomial in here, right there before the exponential as a coefficient on this exponential. So, yeah, typo. I'll fix it in the notes, but we're going to press forward here with the video. And then r prime of t is going to look like, I'm just differentiating r of t, so there's going to be two applications of the chain rule to get me through these three levels of embedded functions here. The derivative of sine is cosine. The derivative of this inner exponential is that exponential. The derivative of the inner polynomial is 2t. And then differentiating this expression with respect to t is a simple product rule expression, and we get that. So here's f hat of r once I insert my extra coefficient of a trig function here, and here's my r prime. The next step is to take their dot product, and I can already see that this is a drag. This is not getting better here, and this is going to be just ridiculous. I'm going to start needing butcher paper so I can actually write out this vector dotted with this vector. And in fact, this one's even worse than it looks because we're missing an expression for now. So I don't like this. I'm not going to be able to integrate this. It's insane. So I'm going to try something else. I'm looking at a line integral of a vector field, and I've just learned about the fundamental theorem of line integrals, and sometimes it makes line integrals of vector fields a little bit simpler. So I'm going to try to make use of that to turn this ridiculously terrible problem into maybe a less ridiculously terrible problem. So, to make use of the fundamental theorem of line integrals, my vector field has to be conservative. The fundamental theorem of line integrals only applies to gradient vector fields, which is to say conservative vector fields. So is my vector field conservative? If it's not, I don't know what I'm going to do. So let's check and see if it is. So I'm going to call the first component function little h. And the second, excuse me, component function little j. These are different symbols than we've used before, but I want to keep little f for the potential function, so I'm just naming these little h and little j. The trick is that the first component function's partial with respect to the second variable, so that would be h sub y, needs to be equal to the second component function's partial with respect to the first variable. That would be j sub x. And if I take those partials, I do see that they're equal. I'm getting 4y plus e to the xy plus xy e to the xy for both of those. So f hat is conservative. The fundamental theorem of line integrals is going to apply, and maybe we actually have a shot at doing this. So we are going to need the potential function for this conservative vector field, little f. The fundamental theorem of line integrals tells me that the integral of the gradient of little f is just going to be given by the value of little f at the endpoints. So I'm going to have to find little f. And this is something we practiced a few lectures ago, finding the potential function for a conservative vector field. In fact, this is why we practiced it, so we could make use of it here. So the definition of f hat tells me that the first partial of little f is going to be the first component function of f hat. That's what it means for little f's gradient to be f hat. The first component function of f hat must be the partial of little f with respect to x, and the second component function of f hat must be the partial of little f with respect to y. So I write down those two equations, I label them so I can reference them. They look about the same to me. I don't see a preference to integrate one versus the other, so I'm going to integrate the first one here. And that's going to tell me that if I integrate little f sub x as given in equation 1 with respect to x, I'll recover little f. Little f sub x is 2y squared plus y times e to the xy. And if I integrate that with respect to x, I'm getting a 2xy squared here. 2y squared is a constant. I pick up a factor of x. Integrating this with respect to x, I'm just repackaging the constant y up in the exponent for this exponential. And my constant of integration is actually a function of y here, since it's a partial integral, we might say, or it's an integral just with respect to variable x. So I pick up a constant with respect to y for this indefinite integral. Now, I did this by taking equation 1 and integrating with respect to x. So I started here and I backed up to little f. Now I'm going to go down the other path and I'm going to find a new expression for f sub y. So I'm going to take the partial of this with respect to y, and then I can compare that expression to this expression for f sub y. And by comparing those two, I can solve for my c of y term. So, taking a partial of the expression for little f that I just derived with respect to y, I get this. I can look at the equation 2 here, my second component function for big F hat, and it tells me this. And comparing these two, I see that c prime is 0, so that c is a constant, and I can choose that constant to be the constant 0. I just need one of the potential functions out of the infinite number of them. And it is my preference to choose the one which is analytically as simple as possible. So I take my constant c to be 0, and now I have this expression for little f. That is coming from here, where I've taken c to be 0. So now I have an expression for a potential function for big F, and it's little f equal to this. And it does in fact satisfy that the gradient of little f gives me big F hat, and you can double check me on that. So take a partial with respect to x, take a partial with respect to y. The vector that you form should be the original big F that we started with. So we have now our potential function, what is essentially our antiderivative. And now we can calculate this line integral by taking the value of the potential function at the final endpoint minus its value at the initial point. So the fundamental theorem of line integrals is going to let us find this expression. We're going to need our r hat of a and our r hat of b so that we can find f of r hat of b minus f of r hat of a. How you do these steps, there's a lot of variability. I'm going to go ahead and find r hat of a and r hat of b explicitly because at least one of them is a little bit complicated. And then we can plug these into little f to find our integral. So here's my r hat that I started with. We were going from 0 to pi over 2. This is my a, and this is my b, 0 and pi over 2. So r hat of a is r hat of 0. If I plug 0 in for t, I'm going to get sine of e, comma, 0. And if I plug in pi over 2 to find r hat of b, I'm going to get sine of e raised to the power, pi squared over 4 plus 1, and then another 0. So finally, the fundamental theorem of line integrals tells me that, well, the line integral of f hat is just the line integral of the gradient of little f. That's because the gradient of little f is big F hat. And now the fundamental theorem of line integrals tells me that that integral is equal to the potential function at the endpoint, the final endpoint, minus the potential function at the initial endpoint. And I had the order wrong here, so scratch that. We're looking at little f at this r hat of b point minus little f at r hat of a, where a was 0 and b was pi over 2. And I can plug those into f. F was 2xy squared plus e to the xy. So here's my x values, here's my y values getting plugged in. This parenthetical expression is f at r hat of b, and I've got minus the value of f at r hat of a here, where r hat of a is this point, sine of e comma 0. And I end up with 0 plus 1 and 0 plus 1. So I'm actually getting 1 minus 1 equals 0. The final answer is relatively simple after the madness of the problem itself. So we were asked to find a line integral of a vector field along some contour. Both the vector field and the contour itself were fairly complicated. When we tried to compute that line integral of that vector field, just from the definition of the line integral of vector fields, things got bad quick. Instead, we thought to check whether or not our vector field was conservative. It turned out to be, and so we knew that we could basically find an antiderivative for that vector field, our potential function, and take the value of the antiderivative at b minus the value of the antiderivative at a, in some sense, really r hat of b and r hat of a, just like the fundamental theorem of calculus. Alright, let's have you folks try one of these. So here is a vector field, and here is a contour, a curve C, which is a smooth curve given by r hat, where t is going between 0 and 1. And I want you to find for me the contour integral of this vector field along this curve. Pause the video, give that some thought. Alright, this is an involved problem. Hopefully you spend enough time on it to actually try to get to an answer here, and let's see if you get the same thing that I did. So here's our vector field, and I'm going to go ahead at this point and just check if it's conservative straight away. I know that if it's a conservative vector field, I have some extra tools that will help me possibly deal with it, things like the fundamental theorem of line integrals. In the next lecture, we're going to think about some of the major implications of the fundamental theorem of line integrals, which will give you even more tools for approaching conservative vector fields. I mean to say the line integrals of conservative vector fields. But it's in general in your interest to know whether or not a vector field is conservative. Things are nicer and you have more tools to work with when you're dealing with conservative vector fields. So let's check straight away if f hat is conservative. No more of this attempting the straightforward method. So I'm going to take h here and take its partial with respect to y, and I get an expression, and you'll notice that I can combine the first and the last term here to get 3x squared times the exponential, and I take j's partial with respect to x, and I get exactly the same expression. Right. Oh, there should be a y here, so there's yet another typo. I apologize, folks. There should be a y factor right here, and I'll put it back into the notes. But note that I missed that. When I took the partial of this exponential with respect to x, it should have been a 2xy coming down to make 2x to the fourth y and the exponential. I'll fix it in the notes, but we are going to press forward with the video. But they do match up, and so f is conservative. Once you fix this, they match up. So we have a conservative vector field. We have been asked to find a line integral of this conservative vector field. We're going to use the fundamental theorem of line integrals, which means we need a potential function for this conservative vector field. So I'm going to take h here and note that that's going to be my potential function's partial with respect to x. And I'll take j here and note that that's going to be my potential function's partial with respect to y. I'm going to integrate one of these, and I'm actually going to choose to integrate 2 here this time around. That looks a little bit simpler. So little f is going to be the integral of its partial with respect to y, and the integral taken with respect to y. Equation 2 tells me that f sub y looks like this. If I take an integral with respect to y, I'm just going to get this expression plus some function of x. Again, I'm doing an abbreviated u sub here is how I'm doing this. If you differentiate this with respect to y, you should see that you get back your original integrand, and it's u substitution that I'm sort of glossing over to go from this line to this. So now we have an expression for little f. We got it by integrating the expression for f sub y that big F gave us. I'm going to differentiate that with respect to x, and I arrive at this expression. So differentiating this summand with respect to x involves the product rule, and the derivative of c of x with respect to x is just c prime of x. So here's an expression for little f that I derived from this expression. Rather, here's an expression for little f sub x that I derived from this expression for little f. I can compare this to equation 1 on the previous slide, shown here, and I can see that this must be 0, c prime must be 0, and so c of x is a constant, and we can take it to be the constant 0. And that means in this expression, if I take c of x to be 0, I get that little f is just that. So this is a potential function for big F, And again, you can double check me, you can take the gradient of this little f, and you should get back the original vector field that we started with. Now I could note that my a and b were 0 and 1, so little f at r hat of 0 is 0, 1. Little f at 0, 1 is going to be 0 here. And little f at r hat of 1 is e comma 2. And little f at e2 is going to look like e, that was x, times e to the x squared times y. And I end up with e raised to the power 2e squared plus 1. So, the integral of f hat along this curve is going to be the integral of the gradient of its potential function along this curve. The fundamental theorem of line integrals tells me to take the potential function at the endpoint, r hat of 1, minus the potential function at the initial point, r hat of 0, along my curve C. And I'm getting this minus this, which is just leaving me with this strange exponential raised to the power of a polynomial at an exponential at e in this form. So hopefully that makes some sense. I will fix those typos in the notes, and we will next time talk about some major implications of the fundamental theorem of line integrals. In particular, we're going to talk about the concept of path independence, and we're going to see that if you take the line integral of a conservative vector field along a closed curve C, a curve that ends at the same place that it began, then you always get 0 for conservative vector fields along the taken as integrals along closed curves. All right, I thank you, folks.